our case, that's not very relevant in theory. When the need comes, we'll study that very easily. Right? So now we know that what we mean by linear span of a vector. Then we can easily identify that the column space of A is essentially nothing but the linear span of the columns of A. Right? That's just opens by definition. Definition of column space, and by definition of linear span. Right? If you guys remember, the way we define column space was we wrote the column space of A as V1, V2, V3, whatever, and we define the space column space as alpha 1, V1, alpha 2, V2. That's essentially nothing but the column space. So we have talked a lot about linear span and the independence. When you add that together, what you get is a basis vector space. So let's jump straight to the definition. So definition is simple. It's just basically addition of the independence and span. So let's suppose V is a vector space, or it can be a subspace of R or whatever. Okay. And we have a collection of vectors V1 to V, subset of V. And then this collection of vectors V is said to be our basis. I'm emphasizing the word the A here because in general we can have infinitely many bases. So any collection of vectors is said to be our basis if and only if the space generated by these vectors is the whole of this V. Alright? And this collection has to be independent. Right? For example, in a line, I can have like 10 points which span the whole of the line. But the 10 collection of 10 vectors will not be a basis because they will not be linearly independent. So the second one lies in the space generated by the first one. First one lies in the space generated by the second one. So these two things have to be necessarily true that this collection first of all spans the whole of V. So LFS is the whole of V. And mutually this collection of vectors V1 to Vm are independent. So this is kind of like I'm looking at the smallest collection of sets that can span the whole set. Right? Because each one, if they are independent, V1 is pointing in different direction, V2 is pointing in different direction, Vn is pointing in different direction. So together, they span the whole of it. If I take any less, then I will lose some direction. If I take any more, then that will already be contained in the collection of V. Alright? Let's follow the definition quickly, identify what we can say about something about the whether these vector form a basis or not. So V is the space, just the real line. Right? So following the definition, can we say that the vector, if it's just a real line, then vector 1 forms a vector in it. So S, is this a basis for V? Is this linearly independent? Is LS equal to the whole of R? Is that true? So if I want to show that the whole of L of S is the whole of R, what do I have to show? That I can scale this vector and I can reach to any other thing. Right? So if X is any other thing in the in my space, then I can scale that one with that this particular X to we choose alpha is equal to X, therefore alpha times 1 is equal to X. Right? So I can reach to any other vector in R and be written as linear combination of 1. Therefore, L of S is the whole of R. So this satisfies one criteria we need for this S to be a base. Okay? What else we need? We need that S has to be independent. So that's alright. Is S independent? Is S independent? Well, geometrically we know it's just a one vector, it has to be independent. But algebraically we can prove that if alpha 1 is 0, alpha times 1 is equal to 0, then to prove that it's independent, we have to prove that alpha is 0. That's trivial, right? So alpha times 1 is 0, alpha times 1 is alpha, therefore alpha is 0. So it implies alpha is equal to 0. Right? So we have that this collection of set S is independent as well as spans the whole of R, therefore this is a basis. Right? So this is certainly a basis. Next one. For a similar argument, instead of 1, you have minus 1, same kind of thing here. I can, if I want to reach x, I can say alpha to be minus x minus x and work out fine. So this is also true. Let's quickly work it out. So L of S is equal to the whole of R, because for any x, choose alpha to be minus x, therefore we get alpha times minus 1 is equal to x, and S is independent. Because alpha times minus 1 is equal to 0 implies minus alpha is 0, if minus alpha is 0, alpha is 0. Right, so this is also true. So this collection of S is also independent and again spans the whole of R, therefore this is also a basis for this particular vector space V, which is R in this case. So from this we can easily see that one vector space can have many, there can be many bases for a vector space. So in this case we saw that one forms a basis, single vector 1 forms a basis, single vector minus 1 forms a basis, and any one vector in R, single vector will be a basis, except which vector? Not empty. Except the 0 vector, right? If you just say your S is 0, first of all, you cannot scale 0 to anything to be anything else. So L of 0 will be just 0. Again, if alpha times 0 is 0, then alpha can be non-zero, right? So even 1 times 0 is 0. So 0 vector in itself is neither independent, nor it can span the whole of R, right? But other than 0, I can take 1, 2, 3 thousand minus 1 minus million, whatever. Each single vector will span the whole of R, and this is independent. So always in general, a vector space can have infinitely many bases. So not only many, we have infinitely many. Right? So this all basis. So we know individually 1 forms the basis, individually minus 1 forms the basis, which tends to other form of basis. What happened? They won't be linearly independent. Very good. Do they span the whole of R? So L of S is equal to R. So it satisfies like the half of the criteria we need for it to be a basis, because I can write any other x as a linear combination of 1 and minus 1 half Exactly. So I can write any other vector in R x as x times 1 plus 0 times minus 1. So any vector in x in R can be written as linear combination of these two vectors. So therefore, this L of S is indeed the whole of space, but they are not independent. Therefore, they cannot be a basis. And why are they not independent? Because I can find alpha non-zero. But yeah, so but S is not independent. Why? Because 1 times 1 plus minus 1 times, no, just 1 time. Minus 1 is equal to 0, so that's alpha, that's beta. So I can find some non-zero alpha beta, such that there are linear combination of two vectors is equal to 0, therefore they are not independent, so therefore cannot be a basis. When do we say algebraic definition of two vectors being independent or dependent? No, so if V1 and V2 are independent, then if it's independent only, so independent means if I have alpha 1 V1 plus alpha 2 V2 is equal to 0, then that only can be true when alpha 1 and alpha 2 are 0. But if I can find some non-zero alpha I, such that alpha 1 V1 plus alpha 2 V2 is equal to 0, that would mean that V1 and V2 are dependent. That's what we are doing. So we are doing finding some non-zero alpha and beta, such that their combination is 0. So if this means this 1 and minus 1 are independent. Moving on. We do the same thing with R2. If we take R2, a single vector of 1, 0, will this form a basis? Why not? So we have this, first of all, is this space independent? S is independent. Why is that right? And it's independent because if we say alpha times 1, 0 is equal to 0, or let's say 0, 0, then alpha times 1 is equal to 0, that implies alpha is equal to 0. So this S is independent, right? But that's not all we need for call this as a basis. We have to show that this S also spans all of R2. But here, geometrically, we know that since S is just one vector, ideally geometrically it can span only the line passing through that axis. So in this case, it will be just x-axis. It cannot be the whole of R2. So in this case, should not be. It cannot be a basis. So what is alpha? So L of S by definition is alpha times 1, 0, such that alpha belongs to the set of R. That's